I want to make some comments on the long time limit of solutions to the diffusion equation in order to help you a little bit with a question on the homework. So let's imagine that we have an initial condition which is given by a shape that looks something like, for example, this. So, it's just some wacky shape. And we ask you to please use this initial condition to solve the diffusion equation on the entire real line. Now, we've already explained to you that if you have the Green's function, that you can explicitly write down the solution of this, which is n of x and t is equal to the integral from minus infinity to infinity dx prime of g of x minus x prime and t times the initial condition n of x prime and 0, where n of x prime and 0 is this shape here, right here. Now, and so in order to find out what happens to this initial condition, you have to just solve this integral, which for an initial condition with a funny shape like this one is not untaxing. To help us in what goes forward, let's state that this initial condition has a size. So why don't we say that this size here, maybe let's say that this is the origin, and let's suppose that this shape of the initial condition goes between -1 and 1. So to solve the integral mathematically is tricky, but there's another way to think about this problem which makes it simpler to see what the answer has to be. So what I've done here is I've tried to redraw the initial condition on the previous slide, but I've scrunched it down, I've zoomed out. So -1 to 1 now is right here, and you will see that, and the thing is scrunched out. So now on the next slide, I'm going to scrunch out even more. And so it's getting scrunched more out and more out. So you see -1 to 1 is getting scrunched, and the initial condition is getting scrunched even more. So this is all to say that one way to think about this problem is to say that if I were to draw the line here, and we were to pretend that this were the entire real line, so this is zoomed way out, that if you're standing far enough away from the initial condition, you can't see all of the jiggles and wiggles and other things in it. And instead, what it looks like is a delta function that is a very, very sharp spike that is located at the origin. So this is the origin. And of course, the strength of this delta function is the mass of the initial condition. So I can think about this as being m times delta of x. So it's a spike with mass m, where m is just the integral of the initial condition, so it's just the integral from minus infinity to infinity of n of x prime and 0 dx prime. That is all concentrated at the origin. And then if I were to ask you what the time of this thing looks like, it's pretty straightforward. That is, it's going to just be the time evolution of a delta function, which is, of course, just the Green's function multiplied by the mass. So at long times, we expect that n of x and t is equal to the mass times the Green's function, which is g of x and t. So you might ask, how can I see this result directly from the equation? And there's a fairly straightforward way of seeing this. So if I were to write down the integral that I had written down before, so n of x and t is equal to the integral from minus infinity to infinity of g of x and minus x prime and t times n of x prime and 0. And then if I were to rewrite our formula that we derived in class for the Green's function, so I'm going to rewrite this. It's the integral from minus infinity to infinity of 1 over the square root of dt times a function of x minus x prime over the square root of dt times n of x prime and 0. So what you can see is that n of x, if I were going to now just plot, to show you, I'm going to show this to you in pictures. So if I were to show, so n of x, remember, is this thing which is fairly localized in space. So when the square root of dt is very large, so when the square root of dt is large, and this is large, then this function f becomes pretty constant over the range where n of x prime and dt is varying. And for that reason, I can literally just bring it outside of the integral. So this is approximately equal to f over the square root of dt times the integral from minus infinity to infinity of n of x prime is 0. And that integral is, of course, the mass.